we know there exists a prefix code. But in order to find it, we have to use the tree and then be careful not to include prefix code in it, right? You have to choose only prefix-free words as a code word, right? So that's what we have to do, all right? So, and when you do the calculation, basically, this is it, and then 4, 2 to 1. The number is 9, which is greater than 8. Aha, this is no good, right? Then existence is negated, right? It is not possible to find such a prefix code with this length, all right? But that was the case for binary case, right? When d is equal to 2, right? Let's now try d is equal to 3, right? Then what happens? Aha, then this one becomes 9, 3, 3, 1. 3 to the power of 3 is 27. If we add all of them, it is just 16. Aha, then we can construct prefix-free code with the ternary alphabet. Okay, if we binary alphabet, no such prefix code. Ternary alphabet, possible. Okay, so although now only that you have to do is draw a ternary tree like that, and then what was it? 1, 2, 2, 3. Okay, so 0 here I choose as a prefix code word, a code word, and 1, 0 as a code word, 1, 1 as a code word, and then so these are the length 2 code word, ternary code word, right? And then 2 to 2 as length 3 code word, right? But there are more such code, right? As you can see, all right. So basically, that's it. So, and then this one is the horse example that we have considered. And basically, that was a prefix code, okay, that we have considered in chapter 2, right? All right. And do you have any questions so far? Very clear, right? There is a video also, so if I went through this too fast, you can watch the video. Okay, video is very complete. All right, now optimal codes, okay? Now we call L to be expectation of random variable Lx, okay? And we want to find a prefix code that has the minimum L, okay? All right, so first we need to find the length, right? Even though I use this set notation because of lack of easy to use symbols, but this is not a set, right? It's just a list, right? Because it could be 1, 2, 2, 3, so we have a repetition. If it was a set, it is just 1, 2, and 3, right? But I'm not doing that, right? So just a lack of easy to use notation. I'm using set notation here, but it is not a set. Just a list, okay? Right, be careful with that, right? Which satisfy the Kraft inequality and have the minimum L. So in this type of optimization problem, right, can be programmed this way, right? L is the expectation of Lx, so I use Pi and Li instead of Lxi, right? And subject to Kraft inequality, okay? Right? And I want to minimize this expected length, right? Subject to Kraft inequality, so that this is a prefix code, right? And then here I will use calculus. Well, Cover and Thomas uses calculus, right? And here L's, these L's are integer, right? Positive integer, right? Because it's a length, 1, 2, and 3, and so on. But I will treat this as just a non-negative number, okay? Non-negative real number. And then I can do the Lagrange multiplier problem and then do the optimization for Li. And then obviously I'm not going through this calculus stuff, but as you can see, this is just taking the derivative of this Lagrange equation and then basically utilize this constraint. Then basically you can have this, arrive to the result. In this particular case, basically the optimal Li star is minus log d of pi. Okay? So pi is given to you, and then you have optimal L's calculated using the calculus. Okay? So Li star is minus log d of p of I. Okay? All right, if I use this in the definition of L, which is expectation of Lx, or Li, then basically this is it, right? So if you substitute this one into it, then basically that's the definition of entropy, okay? So this one is the consequence of using calculus. What happens if we have to use description length which are integer? Then this side must be greater than this side, entropy, right? Because that is the case, where we have to use the ceiling operation here. So ceiling of this real number, then if it is let's say 1.5, if you take the ceiling, it is 2, right? If it is 2.9, then if you take the ceiling operation, it should be 3, and so on. So in such a case, then the expected length is greater than the entropy. So, okay, L, which is the expected length, is greater than or equal to h of x, which is the entropy. All right, so we have to take the ceiling operation. Basically, this taking the ceiling operation part is what Shannon's code is. Okay, you find this and then take the ceiling operation, and then you have the length. Then once you have the length, you can design the code. Okay, using the tree. So basically, that is it, right? So d-adic distribution. In this particular case, when d is exactly, d to the minus n is exactly equal to the inverse of 2 to the power of something, or d to the power of something. That is a d-adic distribution. In such a case, optimal Li is exactly the same as minus log d of p of I, right? That was the case where we have the horse example, right? Where d was equal to 2. Okay. All right. So this is another information theoretic proof that L is greater than or equal to hd of x, but this is nothing but using relative distance, right, between two distributions. So since we have done this many times in chapter 2, I'm not going to do it. You can read about it, okay? All right, and the possible procedure to find an optimal code, which is what I have described earlier. Just calculate this, Li, and then take the ceiling operation. That is the Shannon's code. And the Shannon's code in that particular case, where the distribution is given, then from the distribution you can calculate the optimal Li, and then from there you can take the ceiling operation, then you have the length, and so on. Okay? And then here so far we talked about coding for a single symbol, right? Now, what happens if we consider sequence of symbols or sequence of random variables, right? That is the case where we can use per symbol entropy, right? Or the entropy rate, right? So if the IID sequence, then you can use per symbol entropy, right? So basically, h of d, x1 to xn jointly is less than or equal to expected length of this x1 through xn, and that is less than or equal to this joint entropy plus one bit, okay? And if we divide both sides by n, then basically that is per symbol entropy, right? And if we divide this 1 bit by n, right, as we let n goes to infinity, this part disappear, right? So using Shannon's code is very, very optimal, right? If we use a large sequence of length, right? All right, so that's that. And then if we have a non-IID sequence, then we have to use entropy rate. And then the sequence, we have to assume stationary process. Basically, the distribution doesn't change over time, okay? So that's what we have covered in chapter 4. So you can utilize that, then you get all these results, okay? All right, so here I have 20 minutes left. Then we can talk about Hoffman code and the Lempel-Zip code, okay? These are the two very useful coding methods. Many people are using it, especially Lempel-Zip code is what you are using in zip file, right? When you do the zip, you are using this code, okay? So let's talk about the Hoffman code. Hoffman code is very simple, right? Basically, Hoffman code is an optimal prefix code. Optimal here in the sense that expected length is minimal, okay? With the shortest expected length for a given distribution, which can be constructed by the Hoffman algorithm. Hoffman algorithm says this, right? If you are given with the distribution, and then you, once you get the distribution, you order them like this. Largest probability to the smallest. Once you have ordered them, then group the smallest items, group the two items with the smallest probability, right? And then add the probabilities, right? And then you have a list shortened by 1, right? Because you have added them together, right? And then repeat the process again, right? So here, 0.4, 0.2, 0.1, 0.1, 0.2, right? Now I have to find the least probable items, which in this case, these two. So I have to group them first, right? And then add the probability. Then the list have been shortened by 1 again. So it is 0.4, 0.2, 0.2, 0.2. Okay? Then I have to find the two least probable items and then group them. Okay? So I could have, since I have a 3.2, I have multiple choices, right? To group them, right? Any one of them you can choose. The expected length doesn't change. Okay? So that's the algorithm. And then in this particular case, I group these two together, which is 0.4. Now I have a 0.4, 0.2, 0.4, right? So I have grouped these two together, obtain 0.6, and then only two of them left, and then I group them together like this. So that's the algorithm given right here, okay? So construct a tree in the following routine. So Hoffman algorithm is very simple. So first have the probabilities listed in the decreasing order. You can do the increasing order, right? It doesn't matter. But in this particular case, we do the decreasing order. Second, go over the list and locate the 2 indices with the lowest probabilities. And then group these low probable items and add the probabilities and label it for the group, just like we have done already. Now note the size of the list is reduced by 1. Okay? And then repeat the second step exhaustively, again and again, until you ran out of the members. And then once a tree is completed, we can assign ones and zeros. In this particular case, we say upward is 1, downward is 0. Okay? So in this case, the item number 1 is 1, 1. Item number 2 is 1 and down, which is 0. So 1, 0, and so on and so on. Okay? So we have prefix code, which is 1, 1, up, 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 down, which is this one, down, up, up, so 0, 1, 1 is 3, and so on. Okay? And here there is a typo, as you can see. This is supposed to be the length of a code word, right? So what is this number supposed to be? 2. What about this number? 2. What about this one? 3, 3, 3, 3. So 2, 2, 3, 3, 3, 3. That should be this Li, right? Length of a code word for index I, right? And then you could build a different Hoffman code using that rule, Hoffman coding rule. You could end up with a different lengths, different map, right? But no matter what you do, the expected length stays the same. Okay? And then I have the videos, I have such examples covered, so you can watch the video. All right, that's the optimality and the optimality of Shannon code and so on. So you have learned the Hoffman coding. Probably you have learned the Hoffman coding in undergraduate class, right? Even if you haven't learned, the algorithm is very simple, and then I think it is possible for you to do the homework. All right, and Lampel-Zip coding, this is very practical. So Hoffman coding, in order to use Hoffman coding, you have to have what as an input? What input do you need? Distribution of each letter or each word, right, in a text. Finding out this distribution, is it time consuming or not? It's time consuming, right? So here, Lampel-Zip coding, even though Hoffman coding is optimal because it has such downside, right? But here, Lampel-Zip coding is making use of time correlation structure of a sequence, right? As you have seen that Markov chain, entropy rate calculation, and so on. If you have a time correlation, right, you should expect to have a smaller entropy rate, right? And then if you keep more in the dictionary, then you would have a smaller, additional entropy receiving a particular word, right? As the sequence grows, right? So the entropy of a new symbol is going to get smaller and smaller, right? So this is using that, okay? So that's why it is very good. And then it is also very simple and adaptive. And then you don't need to calculate the distribution. So it is very good. So, and then operation is very simple. The rule is just a single line, which is this one. So if you understand this line, then basically you can do the decoding. You can do the encoding and decoding all together. So parse the data stream into segments that are shortest subsequences not appeared previously. Okay, so this one can be described best by example. Okay, so let's do the example. Okay, if you do the example, then you will understand the meaning. Okay, so here the algorithm is very simple, so I can explain this in a single chart. Encoding and decoding, both. Okay, so pay attention. Okay, so let's take a simple example for illustration. Okay, consider a data stream like this. I am exaggerating. So in this data stream, there are lots of correlation between symbols in the sequence. So I am just using A's and B's. A's and B's. Okay? Out of all possible, alphabet letters, I'm just using A's and B's in order to simplify the argument. Okay? So obviously, as you can see, there are lots of correlation, right? Right? So a lot of redundancy. So you can compress. That's the idea. Okay. So this one start from the left, right? So you read from the left, and then you move to the right. Okay. So here, the rule was what? Parse the sequence into segments that hasn't appeared in the past. So what do you mean in the past? So here, time goes from here to this way, right? I'm doing the segmentation. Here, A, which is the beginning of the sequence, this hasn't appeared. My dictionary is empty. So A is new word, right? So I put this word into a dictionary. Okay? So all I have to do is parse it right here. A. Parse it. Now I read the next letter, which says A again. Is this in my parsed dictionary or not? Yes. First one, right? So I have to read one more letter, right? A, it becomes. Is this new in my dictionary or not? New, right? Because in my dictionary, only A is there, right? So A is new, right? How about B? New. So I parse it right here. How about A? Oh, that was my first one. Okay, so I have to read one more. AB. AB was not in my dictionary, right? So AB, I parse it right there. Okay, like that. Okay, so that's what I'm doing here. A, B, A, B, 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 A, and so on and so on. Right? So all I have to do was parse it. Right? So my dictionary grows as time goes on. Right? My dictionary grows as time goes on. Okay? And then this one, first item, second item, third item, I have 11 total items. Okay? And then now I'm doing encoding. Okay? This is the end of the file, end of a message. So I can now do the decoding, encoding, right? So I have 11 items. How many bits I have to use to describe 11 items? Binary bits. How many binary bits do I need? 4 bits, right? 2 to the power of 4. So 16 items I can represent, right? So I can use 4 bits to this index, right? Right? Okay. And then let's do the encoding, right? And then if I have letters, I am just using ASCII code. Let's say, okay, ASCII code. ASCII code is a 7-bit code, right? So that's what I'm doing. All right. So here A is I cannot do anything, right? No compression. So here AA. This is indexed item, first item. So first one, first word, and the new word is A. Got it? Right? How about B? B is a completely new word. I'm not using index, so no compression. How about AB? A was appeared in my index, so it is 1 and B, okay? And then BP. B was my third indexed item, so 3 I use for the first one. B is a new innovation, so 3B. So what I'm doing, I'm using the history, I'm using the index, right? So that I can compress, and then the new part, I'm just using ASCII code, okay? So that's what I'm doing. So once I have done that, basically these are the, encoded output, okay? So this is encoded result, all right? Now you receive these results, right? Can you do the decoding? So let's do the decoding, right? I see A, that's first word, so I just decoded it as A, right? And then 1A, this is my first one, so it is AA, right? How about B? Nothing, so it's just B. And then first item and B. First item is A, so it is AB, right? 3B. Third item is B, so it is PP. How about 2A? 2A, I decoded it as AA, so it is AAA, like that. So I can do encoding and decoding all together. Very simple. And then how much compression was it done? If I use the index, I used 4 bits, right? And then 1 bit for ASCII code, which is a 7-bit. So 11 segment with 4 plus 7, which is 11 bits. So 121 bits to represent the whole sequence. And if we haven't used the compression scheme, LZ, Lampertsev encoding, then all I had to do was each character has to be represented by 7 bits, so it should be 168 bits. Okay, and then basically this is the compression ratio in this particular example, very short. But if we move on with a very large file or article, then obviously I will use more frequently the indexed word. In such a case, I can compress more, right? Right? Just like Obama's language and my daughter's 5-year-old daughter's language has a small dictionary items. Then my daughter's language can be more compressible than Obama's language because Obama's dictionary is much larger than my 5-year-old daughter dictionary. Okay, so basically that's it. And for a larger example, we have to use the computer, right? So basically you can use this computer code that I have programmed like long time ago. And it was done in MATLAB. So I read the text like this and then do the Lampertsev coding. All right, so this was when Jordan was very famous, right? Michael Jordan, right? So it is all about NBA, right? Right? And this one is H1N1 virus, and this one has a lot of redundancies because it is written with 4 letters, right? A, T, G, C. It's a repetition of this. That's the virus code, right? Can you compress this? How much can you compress? And if you run this example, you will see, right? But this is the verbatim algorithm that you use in the zip coding. All right, so if you can copy this MATLAB code into your MATLAB environment, and then you can run the exam. Okay. Right. That's it for today. If you have any questions, let me know. So far I have covered everything for the midterm, right? And on Wednesday, probably I will talk a little bit about midterm, right? All right. That's it.